we are going to solve a differential equation with boundary values, and I'm going to do it two ways. I'm going to do this analytically, and I'm going to do this in Python with the finite difference method, and I forget how to do this stuff, so I'm really making this for me. Let's just get into it. Here's the differential equation. The second derivative of f is equal to x squared minus 2, with the f at 0 is equal to 0, f at 3 is equal to 2. And I've actually done this problem in different ways, so there's that. If you want to see those other ways, let me know. I'll make sure to put those links down below. Now, this one's pretty easy because if I want to, since I only have a second derivative on this side, I can just integrate both sides of the equation. I can write this as, the second derivative of f with respect to x squared, and then multiply by both by dx and then integrate. So let's just integrate. It's not too difficult to integrate both sides of this. I get f prime. The integral of f double prime is f prime. The integral of x squared is x cubed over 3 minus 2x. But then I have some constant a that I don't know what it is. And we'll find that from the boundary values. Now let's integrate again to find f. So f of x, I'll put it as x. I integrate this, I get x to the fourth over 12, right, because the power rule, minus x squared plus ax plus b. That wasn't too hard. Now we just need to apply our boundary values. So f of 0 is going to be equal to 0 minus 0 plus b equals 0. So b equals 0. Now I can apply the other boundary, f of 3, and this one's didn't work out that pretty, but life's not pretty sometimes. F of 3 is going to be 3 to the fourth over 12 minus 9, which is 3 squared, plus 3a equals 2. So now I just need to solve this for a. So a is equal to 2 plus 9 minus 3 to the fourth over 12 times 1/3. So that's that. Let's just plot this and see what it looks like. And I'm going to use Python. Again, I'm not super great at this kind of Python, so I don't do things the best way. This is not the best way to do it. Everyone has their own better way, but I like to do things simply. So I'm using Jupyter Notebooks because we're going to be using matrices, and you can't do that in WebVPython. Let's just jump in here. And you can install Jupyter Notebooks. You could also run Google Colab, but that's what it is. So I got to import my modules first. Import numpy as np. Import matplotlib.pyplot as plt. So the matplot.pyplot is for graphing. The numpy is for matrix stuff, and there's an error as. Okay. So the first thing I want to do to plot this is to calculate a. So I'm just going to type this out. A is, because I don't want to do that in my head. 2, let's see, it's 1/3 times 2 plus 9 minus 3 to the fourth divided by 12, and that's print a. Oh gosh. What did I do? 1/3, 1/3 times all this stuff. That's right. There. So 1.446, that's fine. So now I need to make a whole bunch of x values. I need to make a bunch of f values, and then I can plot x and f. So I'm going to plot x from 0 to 3. So let's make those. X equals np.linspace. Let's say n equals 100. X equals np.linspace from 0 to 3. And I'm going to put n plus 1 values in there. And that's going to make it in spaces, right? Because you're going to have 1 at the beginning and 1 at the end. And that's that. And then I can calculate my f function, f. And this is what's so great about linspace makes an array, And arrays in numpy Python are super awesome because you can just treat them like variables. So I can just type my expression for f using these arrays. So it's x to the fourth divided by 12 minus x squared. So you can do that. Plus a times x. That's it. Now I can plot that. plt.plot xf run. Boom. There's my function, right? That's the solution to the function. I plotted it from 0. You see the boundary conditions are met. Everything's great and wonderful. But now we know what it looks like, and we can do it with the finite difference method for problems that you couldn't otherwise do. And that's why we're doing it. So now let's redo the problem. We know the answer. We can check. So going back to the paper. Not that paper. That one right there. Okay. So imagine that I take this solution. I don't know what they are, but I want to break f into finite values from 0 to 3. I'm going to break these into values. I don't know what these are, but they're points, right? I have finite difference. And so if I want to break this into, let's say, 10 spaces, 10, 1, 2, 3, 4, 5, I'm going to need n plus 1 points, right? Because again, and I'll show you this when I print it out, but we need n plus 1 in order to get n spaces. And then each one's going to be separated by delta x. Now, I can define the first derivative at a particular point by looking at the difference between points, right? So f prime at point I, if I look at the ith point right here, this is fi, I can find the slope here by finding the slope between these halfway points right here. And it's kind of convoluted. I've done this before, but that's one way to do it. So it's going to be this f value minus that f value divided by delta x. So I can write this as fi plus a half, that's this, minus fi minus a half over delta x, right? Because that's the slope using the point ahead of it and the point behind of it. And I can find this for any point. But I need the second derivative. So the second derivative here is going to be the derivative at this halfway point minus the derivative at that halfway point divided by delta x. So the derivative at this halfway point, I can use these 2 points right there. So I can write the derivative f double prime at the point I, and you can also do this with the Taylor series, but I like doing it this way. It's going to be the derivative right there, which I'll just write this as f prime of I plus 1 half minus f prime of I minus 1 half over delta x. And so f of I plus 1 half is going to be equal to the slope here. That's I, so it's I plus 1. So I have f I plus 1 minus fi over delta x minus f I minus fi minus 1 over delta x, all of that over delta x. And so I can pull all the delta x's on the bottom, and I get fi double prime is fi plus 1 minus fi minus fi minus a negative, so plus fi minus 1, all of that over delta x squared, and then here I just combine those terms. So I get fi plus 1 minus 2 fi plus fi minus 1 over delta x squared. So that's my second derivative. So I can find an expression for the second derivative based on all these other terms. Now let's use this and rewrite our differential equation. So I have f double prime is equal to x squared minus 2. I can write this as fi plus 1 minus 2 fi plus fi minus 1 over delta x squared is xi squared minus 2, right? Because there's x values too. They're all finite x values. Now imagine that I have some points here, and I know I don't want to do this for the first point. I want to do it for the second point, the third point, and so forth. But I do need to take that into account. I can write this as a bunch of equations, right? Let's write this as the following. For the first element, it's going to be for f1, not for f0. I'm going to write this as, I'm going to multiply both sides by delta x squared. So I get f2 minus 2f1 plus f0 equals delta x squared x1 squared minus 2. All I did was just algebraically solve for that. Now the next one in the line would look like this. f3 minus 2f2 plus f1 equals delta x squared x2 squared minus 2. And the next one, f4 minus 2f3 plus f2 equals delta x squared times x squared minus 2, and so forth. And you see that I get a linear system of equations. It's a linear system of equations for f1, f0, f2, f3, f4, and so forth. Now, I do have to do something right here. Remember that f0 is a known value. So I'm going to just multiply this by 0. That's my boundary conditions. And then the last one down here, which would be fn plus 1 minus 2fn plus fn minus 1 equals the last boundary condition 3. But I can write this system of linear equations as something that looks like this. M times f equals b, where m is going to be the components of all these terms. F is going to be the vector f0, f1, f2, down to fn plus 1. And then b is going to be these values right here as a vector. And so I get this matrix of all the cofactors times f equals b. And this matrix is actually pretty easy. This matrix, look at this. I have f1, let's look at this one down here. f2 is going to be equal to negative 2 times f, and then I have to have a f3 times 1 and f1 times 1. So we actually get a matrix that looks like this. We can actually write this as negative 2, 1, 1, negative 2, 1, 0, 1, negative 2, 1, and these are all zeros. And then multiplied by, I'm writing this incorrectly on purpose, the vector f0, f1, f2, dot, 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 fn plus 1 equals 0 delta x squared x1 squared minus 2 delta x squared x2 squared minus 2 dot, 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 dot. So I get this system of linear equations, and now all I have to do is take the inverse of this matrix, multiply it by this vector, and I get these values. Now, in order to make this thing work, I need up here 1, 0, 0, 0, 0, and down here 0, 0, 0, 0, 0, 1. So when I multiply this row by that, I get just f0 equals 0. When I multiply this row by this, I get 0 times f0, negative 2f1 plus f2 equals that, which is the same thing I can get up here. Okay, so it's going to all work in that case. But I need to make this n plus 1 by n plus 1 matrix with diagonals negative 2, off diagonals 1 and 1, and then this first one 1 and that last one 1, and then take the inverse, multiply by this, and I'm done. Let's do it. Okay, we got a bunch of stuff that now we're entering the realm of things that Rhett forgets how to do. So let's just do it. Did I have an n up here? I did. I'm going to redefine n. N equals 10. And let's make a smaller, because there are better ways to do this. We're making what's called a sparse matrix, because most of the values are 0. So there is stuff that handles sparse matrices, but I'm not using them. So I'm not doing this the most efficient way because I want to do it the way that makes the most sense. the first thing I need to do is to make my x values that are spaced out there. So let's do this. X equals np.linspace, and I'm going to do it the wrong way, from 0 to, what was it, 3 in. That says make an array of 0 to 3 with n numbers in there, and I'm going to print that. And you'll see here I get 10 numbers, but they're not spaced the way I want, and I don't have 10 intervals, right? I only have 9 intervals. So if I make this n plus 1, then you'll see I get 10 intervals, and they're spaced exactly the way that I would expect them to be. And I'm happy. Okay, so I have my x values. What do I need to do next? Now I need to define my dx, right? Dx is going to be 0.3. But I want to write it in a way. I'll make this a little bit bigger. I feel like that's not big enough. Dx is equal to x1 minus x0. So that way, no matter what I choose for n, it's going to be the difference. I'm going to actually take the second element in the list, subtract from the first element in the list, and it'll give me dx. And that's what I want. Okay, that's good. Now I need to make my matrix M. So let's make that matrix M. We're going to do this in parts. So I'm going to start. I'm not going to set the first and the last corners to 1 yet. Let's just make the diagonal equal to 2. So I can do that with M equals np dot diag for diagonal. And then I'm going to give it some what we call ones, np dot ones. I'm just going to show you. And I want n plus 1 of those. And then I'm going to print that. So that made an n plus 1 by n plus 1 matrix, and the diagonals are 1. But I want the diagonals to be -2. Well, that's pretty easy. -2 times. Now the diagonals are 2. So I made my diagonals as -2. Now I need to make my off diagonals. So let's just add another matrix here of np.diag, np.ones. Now, for those, I don't need n. I need n plus 1. I need n, right? I don't have as many of those. Why does it keep doing that? I thought I'd turn that off. So I'm just going to say n, and then 1 for making it the off diagonal. And when we do this, now those off diagonals are 1. Yay! Now we need to do the same thing. I'm just going to copy this and say plus, and then change that to -1, and that'll be the lower off diagonal. Oops. -11. And now I have that. So next I need to change this to a 1 and that to a 0. So I can do that. Let's just put it right here. M0, 0 equals 1, and I'll print it. So I change that index. I can index the elements in the array by using these 0, 0 is the first and the first. The first row, first column. Now the first row, the second column is going to be 1, so that's M0, 1 equals 0. You see we're getting it all coming together here, right? Next, I need to change that one to 1 and that to 0, so let's do that. Now, you could say, I know that element number, but I'm just going to use the last element, which is -1. So M -1, -1 is equal to 1. M -1, -2, second to last element, is equal to 0. Got it. There's my matrix. Okay. Next, I need to make my B matrix. So let's do it down here. B equals, now, I want it to be the same size. I want it to be the same size as the width of my, and the height of my matrix. And so you could use np.ones or something like that. Sometimes that happens. But I already have x, right? So I can just use my array x. So b is equal to dx squared times x squared minus 2. And let's print b. Just see what it looks like. There we go. So it did it, right? So it took all those x values and it set them, but it's wrong because this has to be the boundary. X, the first x value has to be 0. The last one has to be 3. No, wait, 2. So we can change that. B0 equals 0, b negative 1, the last one. It's better to do it that way because then if I change my number in, it'll still work, is equal to, what was it? 2. And now I fix my thing. That's it. Now I just need to take the inverse of my matrix, multiply it by b, and that's going to be my answer. So let's do that the long way. I'm going to take the inverse of the matrix. I'll call that mi is equal to np dot linear algebra dot inverse m. And let's print it. Oh, I want to print it up here. Print mi, and it won't make sense, but it did work, so that's good. I don't really care about printing that. Now I want to multiply that by b, and I can do that. I'm going to call that my vector f. F is mat mul, matrix multiplication of mi and b, and then I'm going to print f. And there's my solution. That's my values for f right there. Now you can actually do this another way. You can do f equals np. I don't even have to do the inverse. I can do it all in one step. Linear algebra dot solve m, mb, and I get the same thing. Now let's plot this. Plt dot plot xf, same function. You see it's the same. We get the same thing as we did it analytically. If I want to have let's say more points, let's change this to 20. You don't want to go too high because see things get a little big here. But it looks a lot smoother there. There you go. Solving differential equations with the matrix. And this is for you, which is really me, because I'm gonna forget. I promise you. I always forget all the little stuff in there. And like I said, there are better ways to do this, but the most important thing is to break this into finite pieces, and then with those finite pieces, define the second derivative, and then set up a system of linear equations. And once we solve system of linear equations, we can use linear algebra and a matrix to do it. The end.